When calculating the volume of objects with rotational symmetry, standard rectangular coordinates can become mathematically cumbersome. Today, we will learn how cylindrical coordinates simplify the integration process for shapes like cylinders, cones, and paraboloids. In rectangular coordinates, circular boundaries involve square roots and complex limits. By shifting our perspective to cylindrical coordinates, we leverage the natural geometry of the object, turning difficult integrals into straightforward calculations. Cylindrical coordinates are defined by three variables: r, the radial distance from the z-axis; theta, the azimuthal angle in the xy plane; and z, the vertical height. This system is essentially polar coordinates with an added vertical dimension. To convert from rectangular to cylindrical, we use these fundamental transformations. Note that x squared plus y squared equals r squared, which is the key to simplifying equations involving circular cross-sections or radial symmetry. The most critical part of volume integration is the differential volume element, dv. Unlike rectangular coordinates where dv is dx, dy, dz, in cylindrical coordinates, the widening of the wedge adds a factor of r, giving us our dr d theta dz. You might wonder where that extra r comes from. As you move further from the origin, a small change in angle covers a larger distance. This arc length, r times d theta, ensures the volume element scales correctly with the radius. When setting up your triple integral, always remember to include the r factor. The order of integration is usually dz first, then dr, and finally d theta, though this can be changed depending on the complexity of the bounds. Let's find the volume of a standard cylinder. We set our height z from 0 to h, our radius r from 0 to the constant r, and our angle theta from 0 to 2 pi to cover the full circle. First, we integrate the volume element with respect to z. Since the radius r is constant relative to z, the integral of dz is simply z, evaluated from 0 to h, leaving us with r times h. Finally, we integrate with respect to theta from 0 to 2 pi. This simply multiplies our previous result by 2 pi. The 2's cancel out, leaving us with the familiar formula, volume equals pi times radius squared times height. Now let's try a cone where the height depends on the radius. If the surface is defined by z equals r, the height at any point is limited by this diagonal boundary, changing our integration limits. For a cone of height h, the z integral goes from the surface r up to the top h. This captures the empty space around the cone if we integrate it from 0, so we must be careful with our boundary definitions. Integrating with respect to z gives h minus r. Multiplying by the Jacobian, r gives our minus r squared. Integrating this with respect to r and then theta leads us to the standard cone volume, 1/3 pi r squared h. The most common mistake is forgetting the extra r factor. Always double-check that your integrand is converted entirely to cylindrical variables, never leave an x or y inside a cylindrical integral. Quick test: what is the volume element for cylindrical coordinates? If you chose B, r dr d theta dz, you are correct. Option C is for spherical coordinates, which we will cover in another lesson.